Hello, Arun.
Hi, can you hear me?
Yeah, yeah.
Okay.
Welcome to PDA College.
Yes, yes. Let me just do some setting here.
Okay.
Yeah, I'm just adjusting audio settings.
Okay.
Okay. I, I think we can start.
Kumar Patil.
Hello, sir. Yeah, now I'm audible, right?
Yeah, audible. So let us wait for a few seconds. People are still joining.
Sure.
ಸರ್ ಹೆಸರು ಸರ್ ಇಲ್ಲ ಇಲ್ಲ ಒಂದು 30 ಮಂದಿ ಸರಿ ಹೇಳೋದು ಸರ್
Good evening, everyone. Arun sir, join again.
Yes, yes, ma'am.
Okay. Shall we start?
Yeah, I'm ready. I'm ready if everybody else is.
Hello? Am I audible?
Yes.
Good evening, everyone.
Yes,
Welcome to
ma'am, we
the
can hear you.
welcome to the second day of the ATAL FDP on emerging trends in artificial intelligence for smart innovations and sustainable technologies in Industry 4.0. So yesterday we had a very wonderful interaction session on the first day. Now, today, it gives me immense pleasure to introduce our distinguished resource person, Dr. Arun Patil, sir. Sir is currently serving as a principal applied scientist at Cerebrus Systems. He brings with him over 17 years of expertise in artificial intelligence, machine learning, computer vision, and computational photography. He has held key positions including principal engineer at Target, principal data scientist at ShareChat, software development manager at Xilinx, and principal engineer at ETM Systems, where he contributed significantly to computer vision and AI-driven business solutions. Mr. Arun Patil has architected complex media processing pipelines, multimodal learning systems, and real-time AI-driven solutions that have led to multiple patents and pioneering innovations in areas such as retail safety, theft detection, ad management, AI kernel scheduling, and HDR imaging. His passion lies in mentoring teams, building scalable AI/ML solutions, and driving sustainable digital transformation. So, we are indeed honored to have Dr. Arun Kumar Patil with us today to share his expertise. He will be delivering the session 3 on compact intelligence, building efficient multimodal AI systems for sustainable digital transformation from 6 to 7:30 p.m. and then followed by session 4 on hands-on MATLAB sessions on vector operations, probability distributions, and data visualization from 7:30 p.m. to 9 p.m. So I welcome Dr. Arun Patil, sir. And I also welcome our beloved principal, sir, and all the HODs and deans and faculty members of PD College of Engineering and various participants from various institute to this second day. Thank you. Over to you, sir.
Thank you. Thanks, ma'am, for the introduction. Thank you, the principal, sir, and all the faculty members who have enabled and facilitated and given me this opportunity to present. Just a couple of caveats. So all that I'm sharing is in personal capacity, and most of the data, most of the details that I present are openly available. So this is none of the proprietary aspects of my work in different companies will be captured here. All that is presented is readily available on the internet in terms of literature and papers. So with that set aside, let's start the presentation. So yeah, we are covering compact intelligence, which is building efficient multimodal AI systems for sustainable digital transformation. So here we'll cover what are the set of multimodal AI systems today, what are the signals that we can utilize to build smart systems, and then how are we going to build it in a sustainable way? What are the tricks and techniques with which you can lower the compute cost and have a more sustainable thing? So I'll not be able to see the comments. So if there is some comment that I need to answer or question that I need to answer, could somebody just read it out to me? Does that sound good? Okay, I'll go ahead. So we'll see what is this multimodal AI, and how are these algorithms getting built? What is the variety as of today? What is happening in the state of art today? And then how are we gonna put together systems which are really sustainable, as in, right, they're cost effective. It's not about just a couple of demos where things work, but when you really want to build it ground up or deploy it somewhere, the cost or the entire economics doesn't make sense. So we have to see something that is realizable instead of just talking about some possibilities, but not really. Is there a question? I take it as no. Okay. So today it's a data-rich environment, right? We have a lot of things that we have put together. You have multitude of signals. Now big cities everywhere, cameras are installed in your for traffic monitoring and to find violations. There are at certain sensitive cities, different locations, pollution sensors are put. So in general today, the sensor availability is very easy. It's low cost. And because of various purposes, already you have a lot of things. Already we have a lot of sensors and lot of signals available. In fact, this is a scenario of signal overload where you have a lot of things, but you have to see how to build efficient systems with it so that you can utilize and optimize the entire workflow and really get things going in a very optimal way. So what is multimodal AI? So multimodal AI represents the convergence of multiple processing capabilities within a single intelligent system. Unlike traditional AI that processes only one type of data, multimodal AI system simultaneously analyzes multiple things and one signal augments the other. So that way, let's say a pollution sensor will only talk about pollution, but is it because of a huge traffic jam that has happened because of an accident and there are some fumes that are getting emitted, or is it because of a certain peak hour and that is where the traffic is? So that only when you know the next part, only when multiple signals augment each other and give you real meaningful insight is when you'll be able to take real actions. So that is what I meant, where you get these and don't have simple inferences or specific inferences just by text or just by image or just by a pollution sensor or just by a weather sensor. So the key characteristics is simultaneous processing, which means handles multiple data types concurrently rather than sequentially. Contextual integration. So like I said, right, what is the context of that high pollution there? Is there some breakdown? Is there some leakage, spillage, or this is a peak hour and that is where you see a spike in the pollution levels? Combine insights from different modalities to form complete understanding. Adjust processing based on available data sources and environment. So how do you smartly run those algorithms? You don't have to run the entire thing. So if a certain signal can preempt and say that the next stages in the pipeline need not be run, then that's the best thing for you. So we'll see some examples of that also. And ultimately, it should help you in real time. You should help in insights that come in real time or semi-real time, and you should be able to act on that. So that is what is the key characteristics or the requirement or a wish list of a multimodal AI system that you'll build. So what are the kind of data that we have, right? We said there are so many sensors, so much signals, but all of it is a story of its own. So you have time series data, like wind direction, like traffic levels in at a certain junction. So that is all time series data. There is tabular data. So which means the slight difference between time series and tabular is you may not have signal at every second or every fixed granularity. You could have a signal in the morning, say rain as a signal. So it rained today, then after 5 days it rained. So you could convert it into a time series just by filling holes, but there is a next level of signal information there. Then there is text, there is image and graph. Graph especially if you want to analyze traffic in a city, one thing leads to another, right? Each signal and the jam there, or traffic levels there is not a root, not a cause and event in its own. It is transition of multiple things, multiple roads leading to that junction, and that roads coming through something else. So these are signals, or this is how you will get real world data. And if you're gonna integrate and make some real sense and create some actionable insights from this, then you'll have to engineer and understand each of this. How is it gonna come? How are you gonna fuse all of these and get things going? So just to give a gist of it, if you have some time series data, you'll say, okay, let me just take last 10 samples and create a feature vector of that. I have an image. We'll walk through image encoders and other things where you will you convert that full image into a structured data where you also convert that into a feature vector. You have graph like we described. Each junction you can describe using graph convolutional neural networks, or there is a strategy called random walk, where you can try and now describe each node with feature vectors, and that feature vectors will help then can be put to a classifier or fused with all other feature vectors that are coming here to generate insights. Text we already know well now with a lot this chat GPT era. So these are things just to give a gist of how each signal throws different challenges at you and the needs of each of them. So let's go with the easiest one and the most explainable also, which is say image and text modality. So I think this is a very popular, the screen snapshot that I have here is a very popular algorithm called CLIP. I think most of you might have heard it. So if you see here, there is a text encoder and an image encoder. You have an image, the data set here is an image and the corresponding textual description. So if you have n images and corresponding n textual descriptions, the expectation is that each of them generate embeddings. And then you do a dot product here. So you see here I1.T1. The dot product should be highest for the corresponding images. So if there is an image of a dog, and then you have this, the breed of the dog mentioned here, that should score highest versus, an image of a dog and a description like a tractor or a description of a bus or description of, say, a cat or a buffalo. So the objective or the optimization objective is pretty simple. You take, say, n images and their description, and you try to maximize the dot products of the corresponding image text pair and minimize the dot products elsewhere. So now with the advent of internet data, this was easier once you have gathered so much data, and there is so much interaction with the data today with images. And there is a lot of tagging of images, be it Instagram, be it Flickr, and other places. So this age of internet made this possible. This is already 4 or 5 years old. So if I sound old already. So with this already, you built an image encoder and a text encoder. This was mostly usable in a retrieval sense, or you could build a simple zero-shot classifier. So what you can do is say you only want to classify a cat or a dog. So you just say the photo of a cat and then say the photo of a dog. You feed it to the text encoder. And then you get embeddings from the text encoder for the description, a photo of a dog and a photo of a cat. Now, when you feed an image through the image encoder, you do the dot product and see which scores maximally. Is the dot product of that image with the text encoder's feature vector corresponding to the photo of a dog, does that score more, or does the one with the cat score more? So now it becomes a comparison. So if you beforehand know your system is gonna be shown only these things, it's not like any image under the sun is needed. Sorry, anything under the sun is needed to be shown here. Then this right away renders itself to become a simple classifier. And you could also do a retrieval. So you generate embeddings from the text domain. And then if you have an album of 1 million images or album of 2 million images, you already pre-generate embeddings from the image encoder and keep it. Now you can do a simple nearest neighbor search. So that is how an image retrieval works. So if you have already indexed, so-called indexed, as in you have generated embeddings for 1 million images, and kept in a database. And now you say, get me the images of an helicopter. Or you can also say, get me an image of a blue helicopter. Then the text on the fly, the only thing that happens on the fly is the text encoder that runs there. It generates an embedding. And then in that database, generally like an elastic database, and these days vector databases are becoming very popular. So you would have that nearest neighbor search implemented there, and you would get the most similar set of images, which would be most likely be helicopters or certain angles or certain variants of flying objects in worst case, if you do not have helicopter in your corpus. So this simple thing was just enabled because there is a lot of internet data which is already automatically tagged based on different things, and you already got this going. Moving on. Now let's look at much more complex things. So we just talked about simple image and text one. And on similar lines, there is a model called language bind. And there is one from Facebook called image bind. So you could see here, they are trying to bring multiple modalities in the same embedding space or feature space. So you have video, you have infrared, you have depth, you have audio, and let's say some other modality. Each of them have their own custom encoders, which will generate feature vectors, and you have contrastive learning, which means infrared image, the feature generated by an infrared image versus the feature generated of the same view from a depth sensor, and a simple image or a video should all end up having similar feature vectors or embedding. So this is also like an alignment where you bring all the modalities in the same domain. So that way you will be able to understand the feature vector in the same modality, and then all those modalities are linked to text modality. So then you could derive descriptions from any of them. You could also do retrieval from image to infra to image to text, even image to audio, video, image to audio also, if there are certain actions that are evident. If a train is taking off, you don't need video generally, you can guess that it is a moving train. So then the sound of the moving train would very well correlate. So you could also do some retrievals here. So there is a conscious alignment that is happening in this case. So this is one thing. Another part is missing modalities. Let's say for a certain scenario, a sensor goes down. A sensor goes down. So that is indicated by, certain modalities are not there at certain instances of time. So you have to make do with only those available modalities that are there. So in this case, let's say in the first instance, modality 1 and 2 is there. In the second instance, all 3 are there. In the third instance, only these 2 are there. So in this case, you will have to have different strategies where you are able to manage with missing modalities or corrupted modalities as well. You could have some, checks and balances implemented where it says, the sensor's reading was wrong. So then that is where you have to look at. So then you could have certain embeddings of feature vectors generated. But the good thing is, because of the previous alignment stage, some of those missing modalities can be just managed by simple correlation, or you could initialize them simply. And then the model will be able to, you could do some smart initialization of the missing modality, and you'll be able to still make inferences. So similarly, if you see, the other one is, if you, with the previous stage that we did, if we are able to do some mapping, and if you are able to build some generative models which will mimic or recover the modality 2 from modality 1, can we have a generative model which will mimic the depth signal from a simple RGB image? So that is another way of capturing this. But any system that we will look at, real system which you want to really work properly, you'll have to factor in missing modalities as well. So next one is obviously the core integration challenges, processing multiple large data streams through complex deep learning models is inherently resource intensive, right? Making many models too slow or expensive to practical deployment. So you have to consciously choose how will you use each signal, and any new modality should be really adding that extra value. If it is not adding that extra value, then there is no point. You'll waste all the encoders that you plug into those extra modalities, and the fusion also will take that much more time, and all your data movement also in bringing that signal data into your system is also going to cost you. So there is a multi-pronged cost, right? Data cost, embedding cost, encoding cost, fusion cost, and then it may not be of much value. And there are certain smart ways where, though it is a fused modality, you take a few layers, few signals, first do first level signal classification like a weak classifier, and if that itself says you need not proceed further, then you don't have to run the next level complex algorithms. So key takeaways is, solving these challenges is not, so what I was trying to make a point here is, there is no fixed recipe where you just say, okay, I have this framework, just integrate whatever 10 sensors, different modalities, and it'll work. It is better each of them is thought through, the value of each signal or sensor is realized, the stage that they had to be brought in, and the fusion at which they will blend in and combine or fuse with the rest of the signals, and the computational cost at which they are coming. All of them have to be well thought through, and that is where the human in loop will come in. We can't, today we assume that we'll just put everything to ChatGPT or Perplexity and it'll do it for you. But you have to consciously think through the entire flow. And what system will you bring in? How is the data flow? How are you going to house all those signals? What is your compute processing pipeline? You have to think of all of those things. So this is just the similar bird's eye view. You could have multiple modalities and you could fuse them. You could simply concatenate them if they are simple signals. If they are unstructured data like image, audio, video, depth, IR, and other things, then you'll have to have encoders that generate it. And you also have to choose at what stage you want to integrate them or fuse them. So you want to fuse them in the input stage itself. You want to fuse them in the intermediate stage where you get something out of the encoder and fuse them. Or you want to fuse them at a final stage where already a lot of decision making is happening and it has generated a feature vector. And then you have multi-layer perceptron, which makes just the last few layer lightweight inferences. Sometimes this may be useful if your signals are wide apart and you don't want to move around all of this data to a central thing. Like if you don't want to transmit all the images on an edge device, you would rather want to condense it into a much smaller vector, or say a video also, and then let the receiving module just get very compressed condensed feature vectors, which you just use to make decisions instead of trying to transmit all the images all the way to your cloud server and then bearing all the costs of the transmission and the data storage and retrieval. So yeah, just revisiting again, fusion strategies, right? Input. So data concatenation into a single sequence, which is unified, and then you have unified textual prompting for LLMs. So this enables end-to-end interaction. The cons is it is inflexible, computationally expensive, and not robust to missing modalities. Like I highlighted that missing modalities are very important. Management of missing modalities is very important. So we'll have to do that. In intermediate is where you see if a sensor is simply giving you last 5 days of temperature in different buckets like midday, morning, and night, and some air sensing value, then you can just represent it as a concatenated feature vector. So 7 into 3. So you have just 21 feature vector values of say temperature. You have 21 values of say wind direction or light level, and then you could build a simple XGBoost model and then go about it. So for everything you don't need, but that is where the judicious choice of decision making comes in. What is your sensor giving out, and how complex or straightforward that signal is to fuse. So next level is addition or concatenation of feature vectors, and then you can do it with self-attention and cross-attention and gating mechanisms. I'll cover that in a little more detail in this. So we need a balanced approach, allowing specialized encoding and rich interactions. And that is where the design of, especially with this LLMs, we saw that simple cross alignment was easy, like we did in CLIP and image bind. But if you want a collective information of both the image and the text and how are you going to fuse them, and then ask the model to tell you something, then we'll have to do some kind of smart attention, self-attention and cross-attention mechanisms. We'll go through those as well. And finally, output is mostly about ensemble. So one sensor is saying it will rain, another sensor is also saying it will rain. So then you could do some kind of a weighted averaging or ensemble of those to say, okay, it will definitely rain or something like that as an example. So that is what we are going to see. And if you see, this is input, output, intermediate and output. And so that was about fusion. This is about alignment. How are you going to align them? Because only when you align, you're able to fuse them and do the processing. So again, cross attention becomes an important thing here. And there are other things that we'll look at. How we have to create a semantically coherent shared space to improve interpretability. And cons can be computationally intensive and require careful objective function design. So that is one thing. And component output is using one component's output to guide another. So which that also we look at when you do some embedding based retrieval for LLM prompting. So the next part is transference. Transference is how do you manage time series and image modality conversion or LLM based generation of textual context and modality augmentation. And another is text based series retrieval. So EEG to text conversion. So EEG is a time series data. So how do you then bring in the description of that? So again, that is another challenge on how we are going to manage all this. Moving on. So let's start. So I'm directly discussing the attention mechanism and all that because this is the state of the art. We could have gone through, I mean, then the session would extend. You could start with what you could do with the simple decision tree, what you could do with simple MLP layers, and then what you could do with transformers and attention mechanism. Just because we wanted to cover a few more topics, I'm just directly jumping with the transformers key block, which is the attention block. So if you see here, as of now, most of us read it or study it in terms of just the text-based thing where, each of this, the text is tokenized and each of the token is represented as a vector. And then you have, let's say, how are you is a word, then how are you, all three of them come as vectors, or in this case, the sentence is the big red dog, right? So for each of them, you have feature vector. They go through a set of transformations via the K, Q, and V transformations, which is the query, key, and value. And then you have dot product of query and key. And then it is used via softmax to do some kind of a weighting. So ultimately, if you see here, you are trying to realize how important is one word with respect to other. So because the KQV, all of them come from the same set of words and their token and embedding representation. And when you're doing dot product, you will find out who is what word is important. So the here is really talking about the dog of all the things. So that is, sorry. Okay. So you could see those attention parts. So this is the attention vector here, and that is visualized in this color patches. So you have the KQV, you have the query and key dot product, which will serve as a weight to evolve the values. So you do a weight, you get this weight, do the weighted average of all the values to arrive at the new three transformed embedding representation of the same words. But there you have gone through one attention mechanism, and then there is a multi-layer perceptron which further helps you fuse, and then you could build a classifier, or you could feed it to the next attention block, or you could feed it to the next encoder or decoder block of your transformer based on what you are running, whether it is a BERT model or a GPT-2 model. Going next, this is slightly important to what I'm going to cover next. So let's go there. So this was about text. So if I had just missed a few blocks, it is about text converted to tokens, and then each token is converted to embedding, and this is what is. For image, as we know, this image is, in this case, if you see an illustration, it is broken into these chunks. Each of them you do a linear projection and then feed it to the transformer block. So here, from the transformer onwards, either it is getting the feature vectors from text via tokenization, or it is getting this through this. Both of them is how the values of the attention vectors are calculated. So so this entire thing is learnable. So V, K, and Q are trainable parameters or matrices who will be learned via backpropagation, and all of them are learned. All of them, the input to all of them is this vectors coming from the tokens, and the way you enable this mechanization helps the model assign a specific role, right? It's all because of backpropagation. You have just given 3 matrices, and the way a matrix, say K and Q, and then the next operation that you're defining is a dot product there. That in a way helps them evolve in terms of what is the expectation of what learning needs to happen in K, what learning needs to happen in Q, and what learning needs to happen in V. The learning in the V will help it transform this vector accordingly. So these are in a way transforming the same input into different forms to serve different purposes here. So I hope that was clear, Aniket. So let's go. So same thing happens in the case of image, just that the image is broken into patches, and then you also give the position embeddings here. So it says this is the 0th patch, first patch, and you also give a flattened vector of the whatever is there in the image, and then rest of the thing is the same attention mechanism works here, and then you have a MLP and then a classification head. So now when we want to fuse, so this happily does as a transformer, we have vision transformer, and this one happily works as a, I mean, this is just an attention block, but if you put tokens and inputs here, you will have a text-based processing. Or this could be a BERT model which is doing some classification like sentiment analysis. Is this sentiment positive sentiment or negative sentiment or neutral sentiment? So, but when you want to bring this together, you will have to think about certain computational complexities. So if you see here, there is a dot product that is happening. So if the length of your sequence, or this is a sequence of 4 things. So your attention scores, if let's say this is M, then the size of your attention vector or scores is M square. So the complexity perspective, it is of M square, right? So how are you going to handle this? And especially if you so many patches of images, and as the image resolution increases, you don't want to shrink the image also, because you'll lose the granularity or detail in that. At the same time, if text also has so many tokens and so much sequence, and this one also, and they scale quadratically and they're not scaling linearly, right? So for 4 it is 16, for 16 it is 256. So think of how quickly the computations really climb up. So that is where one of the very popular paper, but already old, almost 4 or 5 years old at least, comes up with this idea that let's think of it like a cross attention. So your output is driven by the number of queries and not based on things. So if you have query as a different vector, and then you do, so see, let's say V and K is coming from somewhere else and Q is coming from somewhere else, your output is always equal to corresponding to what is fed via the Q as the input. So that is the length part. So they have given an example now that if you have a slightly different modification where your input and outputs are different, the 2 key inputs, which is the query and is different, then you can see that you will be able to condense it to a smaller form irrespective of the size. So think of this as the original image. You have broken it into chunks. This is a pretty big image. Let's say you've broken the image into, say, so they say M is pretty high here, right? 5176. Now you want it to be condensed or very limited. So what you want it to be limited is just say, let's say an example here, it's very easy to explain. It's 3 here, a sequence of 3 vectors. Here it is really high. So now you initially randomly initialize it. And then your K and V gets evolved from this, your Q evolves from this, and then you have this cross attention mechanism. Then you have condensed, but while doing this condensed job, you're saying, hey, I have initialized it randomly. I get some cross attention based evolution of these in a condensed form. Then we have a transformer which helps in further evolution within this space. So you've gone from this embedding space and you've come into this condensed space. So what they do is again, they put a block similarly and try and do a cross attention mechanism. So this way, you can see that this perceiver resampler module has condensed a high token count into a small number of tokens. So here, if you divide the image into 16 blocks, there are 16 tokens. If you divide the image into 256 blocks, there are 256 tokens. But you could limit this to just 10 tokens or 12 tokens, and then use the smart flow and then put a classifier like you do in the transformer block, the VIT module, and then this serves as a very good purpose. And they showed that this accuracy was also more promising. And that is where they said, hey, if you're doing this, why don't I fuse this or augment this into the fusion block? So this is where an LLM and the vision modality is coming together. So you have a dog image and a cat image, each of them go through the block, the vision encoder or the perceiver resampler block. Let's assume there is some first level of token evolution, lightweight models. Here, output is still a large number of tokens, right? Because you divided the image into, say, 256 chunks, and all of them evolve and come. And this is where you get to condense them to, say, from 256 to just 10 or 8. And that is what these resampler blocks put it. And then either you can put them in this form of cross interaction, where there is a cross attention mechanism, or these days there are more evolving things where they just sequence it. So you can see that the sequence here is image, the image related signals, feature vectors, and then the text, and then the next image. So this is a very cute dog. You start with the dog image, and then you feed and this is when you train. And generally, if you are aware, these models are trained in the next token prediction scenarios. So you have now fused the modalities. They appear as a sequence of embeddings evolving out of text-based tokens and the image-based condensed feature vectors coming out of this resampler. So that way, we are able to fuse and arrive at a fused modality here. Okay, so this was the snapshot. I mean, there is huge literature on how fusion evolves, and a lot of things have happened. And there also, I only tried to focus on the transformer and attention mechanism, and especially the cross attention mechanism and how that gets along in the perceiver resampler. There are a few much more things in terms of how we would have gone through these things. Just slightly switching gears now. We know all this, okay, there are a lot of literature, there is a lot of people have shown that you could do all this multimodal fusion. While there are considerations in real system buildings, we know technically these are feasible and possible. So we go to the next challenge now, which is today, with all this AI revolution, if you see the cost of getting this done, the cost of training, the energy spent, the real cost in terms of money, sometimes it is rivaling different companies and their spendings. So this is a large AI model, so I don't want to tell. I mean, everybody would know what is the first chat or a large language model that comes to your mind these days. So, without taking names, so you could see the cost here, right, in terms of terawatt hour per year, and that is already like 30% of Ireland. So which means maybe it is more than if you take city in Ireland, maybe Dublin is the capital of Ireland, so maybe it is already more than the energy consumption of Dublin, right? Because we are comparing countries here. Cost wise, already, if you can think of, maybe this is the per year expenditure or GDP, and you could see that they're already covering. So while those companies have been trying a lot to solve a lot of problems, but some of them come at that cost, and there is heavy investment today because we know the possibilities, so people are aware of possibilities. So today you might be getting to use some of these services, but internally they might be really costly, and you could have some business projections or somewhere. Now slowly they are creating plans, monthly plans and other subscription plans, where maybe slowly they are going to even out on the cost. Maybe now they are evening out, but 2 years back they might be running at losses just because they want more data and they want more people to try it out. So, which is what always happens in these scenarios. So they could be burning a lot of cash, but really not getting anything, spending a lot of energy. So it becomes very critical for us to just not be bought by the technical possibility and not thinking of the cost and the environmental impact of these things if we just go by what is possible today. So that is where briefly this is what we'll try to cover. How are we going to break those barriers of compute cost? So we'll look at lightweight models or architectures. There is one of it we will cover in the session, in the hands-on session as well. We'll see how we can do some simplification of those. There is post-training optimization. So, okay, you wanted to feed terabytes of data and train very big model, fine, welcome, we'll use it. But as is such big model, we don't want to use or we cannot use, it's not feasible in our solution. So is there a way to shrink it or bring it down? And then how are we going to do other things like smart representation and smart fusion of these signals? So one is model pruning. There are a lot of architectural choices. I've just put this picture because this itself is a topic where you expand and uncover different training strategies like attention mechanism. There is multi-head attention. There is multi-query attention. There is a lot of strategies where they condense and again expand the feature vectors in between. So intermediate stages process only a lesser number of numerical values. So just left this slide for that. Another, I think most of you know very well, is LoRa or low rank adaptation, and this is where generally when you could see the KQV matrices that we saw, which were trained parameters, where you want to fine tune the model or adapt the model. Instead of representing this entire D cross D, which could be a KQ or a V matrix, which is learnable, you decompose them into two matrices whose product will yield you the same size, which is D cross D, but it is like D cross 2 into 2 cross D. So now you have the pre-trained weights frozen, and instead of one matrix, now your input feature vector goes through this first condensation from D to R, then R to D. So this really reduces the number of operations and also helps in backpropagation. So with this, you will be able to train models faster and have fine-tune them to adapt to different use cases. So you have collected terabytes of data, trained a model. Now you want to fine-tune for specific use cases. Maybe it is good at language, it has been trained with internet data, but you want it to be extra smart on finance data. So then you may bring in finance data corpus and fine tune with this low rank adaptation. So your training cost is drastically reduced. Though forward pass inference is still high because you're going through this also and you're going through this, but backward pass, this part is frozen. So you're going only through these low rank adaptations of A and D, which are of the smaller size, right? So effectively it is 2D into R instead of D into D, and generally D's are high. So that will help you really bring things down here. So that is one method for faster training, though not for inference. And parameter quantization. So this is heavily used. Already most of the inferences are not happening at full precision. Most of them happen at half precision or even FP8. And there are now more interesting scenarios or flows which we will cover. So this is one example representation where you have let's look at the representations first, right? Just let's revisit how precision really works. So in FP8 you have exponent represented by 8 bits. FP32 there is one sign bit. You have 8 bits representing the exponent and you have 23 bits representing the mantissa. On FP16 you just get 5 bits to represent exponent. Then there is block float 16, which is 8 bits here. Then you have FP8, and FP8 has 2 variations where you have to trade off between how do you represent exponent and mantissa. So you could have your implementation where you have both of them in FP8, and then the accumulator is obviously because it has to hold the product and sum of such multiple multiplication. So it's a MAC operation that you're doing. So it will hold additional things. So this is where you are trying to do inference in FP8, especially if not for the entire model, but at critical stages. Another thing that happens is when you're losing the range, especially let's say block 14, or there is this MX8 format as well. So you try to chunk your parameters, the weights, into blocks of say 16 or blocks of 32, and you try to arrive at a common scale factor for all of them. So let's say all of them are in the range, it can be easily represented as a multiple of say 1000. So you have values like 1500, 1200. So when you take 1000 out, then you are only challenged with representing 200 or 500 at a certain choice of granularity. So I gave a simple example of simple additive part, but in this notion of exponent, let's say you are compared to FP32, you have only 8 bits in this case, or maybe I'll take an example of FP8, E4, M3. So in this case, you have only 4 bits of exponent, while an FP32 you have higher, I think. So in that case, you could group a set of 16 or 32 values and arrive at a common 8-bit exponent. So effectively, this gets extended by 8 bits. So 8 plus 12. So then you get to represent exponent with 12 bits. But what you have done is you have really shared that exponent across a set of values. So that is where there is a format called MX8 where you're going to use this, and at a block level you're going to store, and then smart architecture is needed to really utilize this, or map them back at critical computations or multiply it smartly. Your MAC module, MAC as in the multiply accumulate module, has to be smartly designed so that it really factors in all this and still maintains the numerical consistency across. Though the representations are changing, you're playing around across with these different representations, but you get to do those things there. So the next one is obviously the knowledge distillation. So you have a large model. Obviously you like the functionality, the accuracy of it, but you can't afford the computational cost of it. So that is where, instead of trying to train with the same huge data for a small model. So I think there is a huge set of literature on scaling laws, on how you train efficiently lightweight models and also transfer their understanding and learning in terms of parameters that are learned to large models, so that you don't struggle with all the parameters on the large model side. That is a direction which goes from small to large, where a small model helps you in choosing efficient parameters in training the large model, because these large models, even with thousands of GPUs, takes 50 days, 70 days to train. So I just missed adding that, but that is one more important aspect. But in this case, we are going from a large model to small model. We know by study and literature that each model, in fact, the scaling law also will say that each model has a certain learning capacity. So you cannot try and train a small model with terabytes of data and expect it to learn. So while you can train a large model with that, and there are a lot more math and science into that, but not going there. But if you want, so let's assume this large model is a catch-all, right? It is trained for internet data. It is supposed to know biology also. It is supposed to know physics, it is supposed to know athletics, it is supposed to know a little bit of finance and all that. But your work or your scenario is slightly focused to agriculture or traffic management. Then you could pick and choose certain data sets, funnel data sets, which is apt or which is suitable for the size of the small model that you have. Taken through the infer through the large model. And here, when we say infer through the large model, we are not just taking the answers. We are actually getting the output logics as to how it's scored for different tokens or the entire vocab size. And then, which means how, let's say a simple example is if you take a simple image classifier, it was classifying for cat or dog. You're not just taking, given an image, did it classify for cat or dog? You are actually taking the probability scores for both cat and dog and asking this model to reproduce the same probabilities. In simple layman terms, you're matching the predictions in the PDFs of the output instead of just trying to train with simple input and ground truth. So, which is what I meant. And this is very heavily used, and this has shown to really give a lot of gains and condense it. But you have to remember that then when you do this, you have to focus on limited capacity or limited tasks for your small model. Don't expect this to generalize across everything the way the large model does, but specific limited functionality or limited domains, this is a good way of getting things or going across, getting a small model there. So we went through different techniques. We can dig deeper into a few of those if any of you are interested. If not, I'm going to switch gears and go to the next thing. So let's say, today we talk about, plants. You could take an image and you could detect what is happening. But when do you execute what? So here is a simple split. Let's say we have put a simple in full 10-acre land. We have just put one sensor array, which means it is a good self-sustainable thing. It has wind speed, humidity, luminescence, light level. It has other things like has it rained? What is the amount of rain that has happened? It has some soil moisture sensor, dug into that. So it is one sensor, and here we are trying to say, or an array of a set of sensors, which is in a way approximating this entire field of land. So, if you know that, it's not going to rain half of the field and leave the half of the field, or it's not going to have different humidity. I mean, these are agricultural lands, right? Unlike you could have different temperatures across different houses based on whether it is beside a restaurant which is emitting a lot of fumes and all that. Here, let's say a simple low-cost sensor can approximate or do a first level approximation of even 10 acres of land. And then we have statistically seen that what kind of humidity, or if it is too cloudy, overcast, and it is humid, what kind of disease are the plants likely to develop, or what kind of deficiencies, or what failure to flower or failure to fruit, what kind of problems can be seen. We could collect a lot of statistical data and say, okay, if this kind of weather pattern has persisted for 10 days, then this kind of plant is likely to develop this kind of a disease. So then you don't have to go and every day scan and take photos of all the leaves of all the images. That is insanely difficult. Acquisition cost is high, processing cost is high. So what are you going to do? So you have built a smart proxy. It is not really, the sensor is not really going and touching any leaf or picking it and analyzing its composition. But based on historical data, a model has been built saying in these kind of environments, this is highly possible that this plant can develop this kind of a disease. So then when this sensing system flags that there is a very high likelihood because such kind of a environment has persisted from say 10 days or 15 days based on the crop and how you want to react. That is when you could pick a drone and fly a drone or go manually and sample a few set of leaves of plants and then grab images, and you could use, with your subscription plans today, you could use even a Perplexity or any other thing, if not your custom trained models for cross modality, which will tell you what has happened and what needs to be done. So that is one part. Or say only at the time of yield you want to optimize. So those critical periods where you are harvesting, you can only there apply these high cost sensors and capture signals. And other times you can happily approximate that. In a way, your high cost sensors become data generators, data set generators for your low cost sensors. Because let's say initially you gather data, you struggle, you take the images, you label them. But smartly, what you have done is when you have taken the images of a leaf and say, if it looks like this is the disease, you also have gathered signals on, okay, what were the weather conditions? What fertilizers, what pesticides were sprayed? So in a collective sense, if you have taken these details, these things help you generate data, which is one-time data or label data, which can now feed to this and free up the cost of using this or free up this from continuous usage. So it's also, so when we collect data, let's think holistically. Let's not only say, okay, my project is an image processing project, so I'll just collect leaves and classify them for diseases. But if you really look at all the co-occurring systems, and that's where we're talking about modality, right? Multimodality. This is the true smart way of using. You don't need high complex algorithms, with complex formulations. When we plan your data collection and data acquisition and how you build your systems with stages where, okay, this macro sensor is a good approximation across the field. But to really react when this is showing a big red flag, or where the cost is really critical. This month, 1 month is harvest time. This 1 month I can afford to go and capture as many images or spend compute cost in cloud where I want to stream a lot of these footages and find out what is happening. So only those sensitive periods we can use this. In other periods, we can happily live with the smart approximation of this entire thing using this macro sensor. The same analogy works for your traffic monitoring and other things. Like initially also when I started, we gave an example of let's say your air pollution sensor has showed it. Now, air pollution sensor readings are very simple readings which you can tap. It's not a heavy data, but every signal, maybe even traffic police has access to other cameras which are put in commercial environments and all that. But how much of the data are you gonna marshal out to your servers, and how much are you going to really process? You have a camera, you spend money, you put the camera there, but how much are you going to really process using complex algorithms? So that is where again proxy signals come in. So you could have simple noise levels, you could have pollution levels, simple magnetometer arrays, which also can tell you what is the density there instead of really going for those. You can use these as the proxy, exactly like we used in other scenario. And if you see something really happening, then you can say, why is this traffic? There is so much of logjam, which is unconventional. It already flags it as anomaly, saying this is not regular to have this kind of a high air pollution levels or noise levels at this time of the day at this junction. So then you can only selectively stream in the footages of those and use complex algorithms. So you can still weave that without human in loop, just that you have smartly woven a system where even now it is still no human in loop. Nobody is saying go and now feed this camera's footage to process, but the system is smartly woven. And again, initially, if you see these cameras where dataset generators or confirmers for this, right? If there is a high thing, is it really because there was a traffic jam? So initially, you use these as smart dataset generators or data labelers for these signals to say, yes, okay, this guy is seeing high pollution. And if I tap to that camera, there was actually a lot of traffic jam there. So initially, you smartly utilize the costlier ones as a data generator or annotator for the lighter weight lighter weight processing modules or engines. And then, these guys help take away the load from this system. And then only when a certain thing happens, you could process the feed, and then an algorithm a complex algorithm can analyze whether there is a road blockage, whether a truck has toppled there, whether there is some riots going on there. So you could have a very smart, very low cost system where you could have a compute capacity at any point of time just of say 10 cameras or 10 footages, 10 feeds, but you're managing, say, a colony or a city of 100 cameras or 1,000 cameras very easily because you're smartly integrated very cheap sensors and cheap processing cost with these things. So I hope so this is further, further description of the same thing. Maybe I could have switched the slide and read it to you, but I think this is what. So with this, already I've given examples where you can see that because you're fusing those signals and you have smartly thought through the entire data collection across modalities, that helps you in drastically reducing your accuracy. So mean squared error generally, which is when you're measuring values. Also, it gets you more context of what has really happened. And obviously, there is a lot of compute cost reduction that happens. And slowly with this, we'll be able to move to a sustainable deployment and really realizing some useful value out of these systems. So I think these are some references. I'll add more before we put this. With this, we can go to the next session. I think I would be inclined to have a short break. What do others think? A 5-minute break, would it work? Or we can walk through any of the slides and answer any of the questions that you have. I don't know what is time now. Okay. Just a second.
Hello, participants can ask if any questions are there in the session one. Any doubts?
So it's 7:07. Can we start back at 7:15? Ma'am, can we do that?
Okay, sir.
What?
Another 5 minutes break. All of you, I request all the participants to stay here. After 5 minutes, please, the sir will be starting the second session.
Yeah. I'm not dropping off. I'm just putting the coffee logo here.
Okay, sir.
Thank you.
ये aquí emang naik tam bari bara ya to baik tam
Hi. Hi. Shall we start? And while we start, one request. So while getting up all these collabs, I have exhausted my GPU quota on Google Colab. So it would be great if any of you can volunteer one each and pick up these. Open these and try and run. Otherwise, I will be able to just walk you through them. I have runs and results here, but if you want to quickly try something, or get a first hand running, we'll not be able to do that. So I've shared as we walk through them. We'll just go through.
Already I have also shared in the group.
Okay, so then I think as we go through, okay, can anybody, any one of you, pick up the first one, which is the clip one. The first one that I shared in that is related to clip.ipynb. Would it be possible for any of you to open that, share your screen? Or I'll just walk you through these things. So let me मोहम्मद है अताए आलमी हिदायत से प्यारे मोहम्मद है अताए आलमी हिदायत से प्यारे Okay, let's try and run. Maybe it will run in the CPU mode. So this is basic. Are we good to go on this? So basically what we are going to do now, just to give you a gist of it, we'll just walk through simple clip model and try and see how it infers or gets you details. Then I wanted to show a good working demo of a model called mini CPM. It seems to have the quality or the accuracy of a GPT-4o or a Gemini 2.0 Pro. And this is the architecture. They process video also. And the resampler that we talked about here, they process it for videos and do some same kind of smart fusion and insert those smart fuse tokens along with this and then process it. So we'll walk through the clip module and how inference is done. We'll walk through this, and any of you like me can just open this. And as an example, just to be careful of what is happening, I had put this already. So if you see, what is good about this is open source. You can clone this repo. You could build a locally hosted thing like this. You could very well do this, or you could plug in other things in the flow. All the code is available on this. So it could be a very good chat environment for you and a handy demo. And I think there is a CPU version which you can run very easily. So because you could choose different lightweight backbones with this. So that is the intent of selecting this and trying to show you how quickly it is able to. So I just put this and I said, what is happening here? Can you explain? So when you do that, it's not showing the text here, unfortunately. So I basically put it and asked, what is happening? Can you explain? And it gave this detailed explanation of what is it. It says it could be this powdery mildew, and this is the thing. So then I asked, what is happening here? What is happening here? What is wrong and how to fix it? So they say this image shows a traffic accident on a busy road, likely causing significant congestion. What is happening here? A large truck, basically whatever, it's just described this. What is wrong? Traffic description, how to respond. So immediate response, traffic management, investigation and all that. So this, maybe I and you are also not able to make out. I just asked, what is this? And is there anything wrong? So it says the object is an image of motor mounts or engine mounts, and these components serve to secure an engine or transmission within vehicle. Is there anything wrong? The mount appear worn out but severely damaged. So that's what it says. So basically potential issues, reduced dampening, engine movement. It is also saying what's likely to happen, right? Just with the picture. So that's what I'm saying. You could host a thing locally. You could replace the LLM model that with which it works to get it fast, and also already try some of your projects which want some multimodal interactions. And if you take this model and further do knowledge distillation, I mean, I can share a lot of repos which help facilitate these days. By spending small compute cost, taking a simple Google Cloud subscription with a few GPUs, you'll be able to have a lightweight model with which you can host something locally with your small GPU. If you bought it for gaming, you could really build and get going with some very nice smart systems, and definitely leading to some smart projects. So just because of the overall compute cost, I'm just shying away from, really. Okay, let's see if it shows something on this. The answers are pretty fast. See, it's also it's also saying it's grapevine, right? It is a leaf of that grape plant. And the leaf has numerous small raised bumps or galls on its surface. These galls are typically caused by insects. So there is an insect infestation, and because of that, weaken the plant over time if not controlled. So monitor regularly. So already it is saying what to do, what to handle, and all that. And this is already a pretty lightweight. They could afford to host it for anybody to try. You could just go here and try it. You will get these things going. And you have the full code for you to host it locally and try, like I highlighted, right? Many versions are there with different sizes. So what happened? Somebody has printed something here. So are you, yeah, so we'll walk through this code. Are you able to execute this, Harish? Okay, that's fine. So I think I already walked you through the clip flow, and all we are trying to do here is, get it to run and see it firsthand. If something like this was hosted, it would have been very easy for us to quickly try things. But at least in this case, the installation happens, you get the torch vision, and in your account, everybody, when they open Collab, I think most of you would have already played with this, so you get some GPU quota every day, and you will be able to run even large models, which otherwise are really not possible for us to quickly try. So they've just shown that, a critical part of your multimodal processing is the text. Basically, the text processing is the text has to first get converted into tokens. So I think the total number of token size or sequence length was this much, but just the hello world was sufficiently represented using these 5 token IDs. So hello world got represented in these 5 token IDs. They just try to show it to check if the tokenizer and everything is in place. And then they have so many textual descriptions. Each of them is related to that image. And in this, I think this is a loop to read all the images and show the corresponding text. And now this is where you're building features. So you take the image input and you encode both the image features and text features. And then we are doing cosine similarity here, the normalizing here, and doing cosine similarity. Then you get the length of description. Now you see across these image pairs, where does it score maximally? So you can see that a page of text about segmentation is what is scoring highest or has the highest cosine similarity with this. Well, it is not the case with others. I mean, likewise, you could quickly change some of these and try your own. I mean, that was the intent of trying to get you or any one of you to run this and see for yourself how well it does. And if you try to challenge it by giving slightly different breed of dogs, and then you can see whether between those breeds it is able to differentiate well or not, or try for something like leaves, or try for something like a nut or a bolt or mechanical component, and try and see how well, because it was trained on so much of internet data, how well did it do. So this was simply picking up a set of images and corresponding text, and verify that those are the corresponding co-occurring texts are really scoring high. But let's say now we want to do for zero-shot classification, right? Because generally with the amount of data it has been trained, it should be able to classify for anything. So I think they've taken this CIFAR data set here, and then I think now with only some of these small things, it did not do well, because this page, it said it is bad. But in this case, Rocket scored high. I think in this case, Cattle scored high. Ideally, if horse was there, that should have scored. So in this case also, you are seeing boy and man are scoring high, corresponding to other things. So this is a quick verifiable thing, and like we said, we went through the architectural block. Each of the encoders will have attention modules, and you could try, or it could be a simple feature generation based, convolution based modules also, especially on the image side. Go through that. So we covered clip. We also quickly covered this. Mini CPM, because it was easy to quickly see what was happening. And they say you could chat with single image, multiple image, video. I haven't tried those because I don't want to risk uploading a big video now and it getting stuck here. So that is one part there. Let's see what else we have to cover. Okay, so fast VLM is something that came, I think, a week ago or 15 days ago. So fast VLM is a vision language model from Apple, and they are saying you can run it directly on iPhone, right? I don't think till now we have any model, especially forget about large language model. I don't think we have forget about vision language model. I don't think we have any simple text only language model or large language model running on phones. But they are able to get this going with some custom architectural changes. And the person who has led this effort has been an ex-colleague of mine. So I had the opportunity to work with him in my initial career. So this came just 2-3 weeks back, and I think speed-wise, this is already on the top. And we tried to hook up a Google collab. Let me try and open that. Okay. So the good thing is by the time I set up everything, I had run out of GPU. But luckily, you could see this model, fast VLM 0.5 billion model is able to run without GPU. It's able to run on CPU. Obviously, they are now saying you will want to run it on a phone. So it would be pretty fast. So I've tried to get an URL here and then ask, and it says the image is a short-haired kurgi in situated outdoors. Okay, so it just gave its setting and where is it generally found. If you look at this architecture, they have done a very smart amalgamation of both the conventional image processing based things like convolutional neural networks and some attention blocks in between. And then this kind of projector is again like our perceiver resampler, which collects it and transforms it to feed it alongside the text-based tokens that they come along. So I'm also going through this fully because this came just a couple of weeks back. But if you see here, you have this block that they have mentioned. The key things is there is a convolutional block here which condenses the image pixels into feature vectors, channels, number of channels. Again, there is a rep mixture stage, which is this elaborate, it looks like very hand designed. And, lot of learnings across multiple years on how to optimize and build convolutional neural networks and different varieties of it is really picked into it. You could see there are a lot of complex stages, different batch norm, 1x1 convolutions, and then fusion. I'm not sure, I'm not going into details because I'm not sure in the audience how many of us have really gone through in detail on convolutional neural networks. So they have this custom, it really looks like custom engineered, really hand engineered a certain kind of architecture to say this is what I should do, this is how features should condense and generate the next features for the next stage. And then finally, this is there. So we could go through a lot of things they have cut down. They have to cut down a lot of conventional flow. They're not going to perceiver sampler. They don't have a full-fledged VIT block. So that's why they have it is faster. So they have hybrid convolution transformer architecture. The speed advantage stems from its fast VIT encoder, which combines the best of convolution and transformer architecture. They have multi-head self-attention block in latent stages, refining high-quality visual tokens. So this is where, like I said, those attention blocks further refine and condense. This hybrid approach generates visual tokens over 4x faster than pure VIT. This also produces 4x fewer tokens, generates 16x fewer tokens than VIN. So that stages like the perceiver sampler will do condensation. So when it comes along with language tokens, it will be much lesser. So they say at this resolution 768, it produces the same token as a VITL of a much smaller image. So lot of these optimizations have really gotten it to do, but the core motivations of modality fusion are all there. But how smartly do you map those pixels? The entire game here is how smartly do you move from pixel domain, like 1 megapixels or more, to a condensed feature space which is able to co-interact or work along with the language to do all the multimodal, this just the two modality question answering, or you ask a question via text and this happens. So that's the flow that we are looking at here. So just take a look at this. And I think if we could run it on the phone also, because I ran it on CPU, you could run it on your laptop. It's not a major deterrent, and there are multiple variants that they allow you to download here. So 0.5 billion up to 7 billion based on how you want to do. And they have low precision model also. So you have like 7B model as well. So this was what I wanted to highlight. So this is the paper. And they've already shown some benchmarks like in the OCR bench. So most of this, if you show a table or a image with an address written, and if you ask via the corresponding text component, what is written on this, it should be able to really read that and show that. So these are the things I had, unless one of you picks up one of these collabs and then we start running and, we try out different things. Otherwise, I think I have captured good amount of content. Otherwise, we can go through all this detailed paper reading, but I don't think this is the right setup for the environment to dig to that level of detail or deeper things. Any questions? Anything you want to go deeper or cover anything? Okay, yeah. So all the research paper links are there. I think I'll put it in the slide. This was also covered. If not, anything specific that you guys want to cover? Like here, you can see how the perceiver resampler is built. And you can also look at what parameters really define them as to, let's say, see, the perceiver resampler is not limited to image. You could have any different modalities which you can map to smarter set of condensed modalities here. So in this case, you can see that the definition is not really talking about just images, but input channels, because it is RGB or specified 3. Input axis, it is they specified how many axes are there, so the two dimensions are there for that. So it's like 2D image, it's 2D, and there are three channels of it. So that is what it means. Num frequency bands, which is generally a hyperparameter here, and number of latents, that is the input embedding dimension. Then attention heads, latent heads this is in the transformer block. Then the cross dimension, and how many classes you want to classify this, because here it is used as a standalone block. So it is doing a classification job here. Then there is attention dropout and F dropout. And you could see this for audio input. Yes. So for audio input, one tricky part is you have your audio, you'll have to convert either into frequency domain. So audio also can be represented as an image, right? When you convert, you chunk the audio into chunks of 16K chunks or lower, and then you generate a spectrogram out of it. That also can be looked upon as an image. Or you could have other smart representations for audio, and then you could feed it. This technique of combining this cross attention, there is nothing special or magical uh, about images here. This is easily mappable to other things. This is a smart way of condensing the information before taking it to the next level of modality fusion. I hope that answers your question, sir. Madam, sorry. So that is why I was trying to say, first thing is you could smartly represent it as a spectrogram of chunks or overlapping sliding window audio samples, and then you could use it. Let's see while we do it if that lets me. Okay, no, that is the problem. So that's the problem. It says I have too many sessions open. So otherwise you could see the output and a classification coming out of this. It's a simple ready-made package that we could use, and you could set off so this is smartly you have initialized the model, and then you could set off a training and see how well this does for your modality. So you can right away build a classifier, just add an additional set of training code here, which I think these days ask. So yeah, so it says perceiver model audio data. We'll need to prepare audio data, adapt the model for this. So load data and process audio data, adapt perceiver model, define training, evaluate. Finish task. So okay, it's already suggesting importing necessary libraries. What do I need to do for this? Okay. I think I already did accept and run. I think it is asking us to give this specific data paths. It already generated librosa based. That's what I was suggesting, right? Bell spectrogram, and in this spectrogram, then it becomes easy now because now it's in that form of being able to put it as an input or like similar to image, just that it's a spectrogram. We have some sliding window of samples. So sampling rate is mentioned, file path is mentioned, and I think Y is the label. I think label of what is it? Yeah, processing traffic audio, process rain audio, and then
Sir, can
sorry,
we use big data for working this on this? Big data?
when we
Sir,
use big data. Ma'am, can you clarify the question?
sir, like samples we are using, no, sir, sampling. So
Uh-huh.
instead of doing samples, complete data set we will take. Our data set is very big.
Yeah, yeah. So see, but then you will need some smart way of. So how are you going to do it? So the simple take the vision analogy, right? So the vision transformer, all they did
Huh.
is they chunked it into say 16 blocks, and each of them they just rasterize the pixels.
Okay,
But
sir.
but audio is too much, right? I think if I remember, sampling rate is what 16K or something like that. So per second, you have
Huh.
per second you have 16,000 samples, and
Right.
1 second of audio is hardly anything. You won't make out what is it. So
Huh.
all I'm trying to say is, I mean, you could, but then just for 5 seconds of data, you will be sampling what 80,000 samples.
All right, sir. That
So
is also big.
so the cost is crazy, right? So already audio, even before all this LLM and all, already people have done the smell spectrograms.
Yes.
I think phonics and all that, right? So they've
All right.
already found a smart way. That simple sampling of audio at that 16K, what you call the PCM data is of no, I mean, it's not directly processable. Even conventional audio classifiers, I don't know how well they do. While you say that, there is a unit architecture called Wave Unit.
Unit.
So
Sir, do
Wave,
we need a library for that?
no, you don't need a. I mean, the conventional ML frameworks
Oh,
is
right. Machine learning, sir.
so this one they have used to do lyric songs to lyrics alignment with this.
Okay.
So here, if you see, uh, they have raw samples.
Right.
Raw samples directly with 1D convolution. They keep on condensing it and then they upsample it. And instead of in your case of wave unit, they cut. See, initially they train it and try and recover the same thing. So what they have done is, you know, as a functionality, there is nothing big, right? They take it, they condense it, and then they recover it back as much as possible, and then they do some simple MSE. And okay, so in this case, what they have done is they have done source separation. So they have separated vocals and music.
Yes,
So,
sir.
and now this in a way is an autoencoder, right? So from all this huge 16K per second, they've come to a small size. Maybe you can cut out the encoder part of it and use this instead of going through the spectrogram route. And here you could have a sliding window of 5 seconds, and that those becomes your tokens. And then you can go feed this block to a perceiver resampler, and then do the other thing instead of going to frequency domain and building the spectrogram. So this will be one good paper for you to
Okay.
So that was one thing.
Thank you.
Welcome.
Sir, for this, can we add hand gestures for this, sir? For
Yeah,
this audio?
you can do hand gestures. Wait, so where was I? I'll just go to what I was running. I think I threw some error. Anyways, so okay, so now the question is, you want to do hand gesture and then plug it into LLM. So
Yes, sir. Yes.
so the conventional thing will work, right? I mean, so you need a perceiver resampler taking one image of your, let's say your hand gesture, you have a window of 3 seconds, and then at 10 frames per second, you have total 30 frames. 30 frames, and then you do the condensation like we discussed, and then you can feed it to this model, right? But then I have a question. If your use case is custom use case, then why waste a large compute? So I assume when you say hand gesture, your camera adjustment is such that your hand should be clearly seen. Why not build a lightweight model for your hand skeleton points like YOLO, which you can run on a simple Raspberry Pi? Now, with that smartly, you have converted all your pixel data into some relative positions of a hand. So let's just generalizing, right? So if we take, so let's say if you want to do human body action recognition, I mean, just transforming your problem from hand gesture to full body action recognition, would it be easy to condense it into a small, to quickly show you what I was trying to say. Okay, so what I'm coming at is now you have two choices, and that is where the smart deployment comes into picture. You will give this video, collect it into frames, give it to that perceiver resampler, and then hook it up with an LLM and do it. But then you have so much cost. Now, what if all that matters, all your hand gesture is like your finger points, right? Finger points and the joints of your fingers with your palm. Similarly, if I just shift the problem to full body behavior, running, sitting, action, all that matters is this key points. So if you have a lightweight model which can run on a Raspberry Pi and generate these key points per frame, and then across frames, each key point across frames, if you track, it becomes a time series data. And then if you feed that as a compressed modality, you have a much smarter way of getting things done. So that entire action, so let's say there are 32 key points there, each of them has an X and a Y, so 64. And you wanted to do for 30 frames, so 64 into 30. That is still much lesser and already critical information for your use case. You see, you don't care what that person is wearing. You just want the key points, right? Because your task is custom. So then the better experiment to try or smartly train the model is extract those feature vectors across those frames and feed it or take it via the augment, the perceiver resampler, and convert it to just one single token and insert with along other text. Basically, in this case, what would be your text? What is this person doing, or describe the action of this person? and then you give this condensed token and try and see if the model can evolve and process. Or take these, put a couple of MLP layers and then do it. That may be a much more smarter and cost-effective way of doing. Then, I mean, technically what you said is feasible, but you may get more brownie points from your prof, or the project may become more lucrative if you are able to do it at such low cost, right? Because then 10 cameras with a Raspberry Pi or something is already emitting just these features of detecting person only when there is a person. It is sampling nicely, taking 10 frames and emitting this. So then your simple, GPU of 1080, like a NVIDIA GPU 1080 Ti of 12 GB memory will smartly do it, and you can proudly say you are able to recognize actions and flag some kind of events for your entire college campus. If you get where I'm going with this. Otherwise, we have the vanilla flow there that we could go through. Does that answer your question?
Thank you, sir.
So try that YOLO model also. It's very lightweight. You could easily port it on a very simple hardware embedded system or. So I'm just saying, let's use it smartly. I mean, these elegant recipes are there, but there may be much more simpler things for it. So yeah, we tried to take the help of our Gemini LLM model to generate some code, and somebody rightly said there is some error. What does it say? Yeah, basically it's an error because obviously we don't have the files for this. I'm not saying there may be not other errors, but at least it looks like it generated some code and then finally has some kind of a processing pipeline that it will.
Sir,
Yeah. Good.
sir, audio data set can be taken any kind of data set, sir?
Any kind, as in, I mean, see, you need the data. So the data set is two things, right? The sample and the label for it.
Yes, sir.
Ideally, it's better to take slightly uncluttered data set. So let's say you're recording at your house and you're actually recording because you can't go and get an accident video, or you can't go and record in a place where a huge protest is going on or people are fighting. So let's say you play some videos and say that is my audio sample. But then if you're not careful, the cooker going off in your house and the cooker whistle will go. So it has to be slightly uncorrupted and crisp. For the 10-second video, if you're going to annotate it is a protest, people sloganing or stone pelting or some other truck falling off, it's better be uncorrupted. And sometimes the tricky part is accurately segment or divide that audio into, okay, here somebody came and the sound of footsteps is there, and this is where the person opens the door, and now you have the sound of the door opening, and this is where the person starts eating with a fork and a knife. So then that sound, the cutlery sound is different. So sometimes annotating is difficult, right? One movie itself can give you so much data, but you have to painstakingly do, or you have to do some smart segmentation where you say, okay, let me divide. I'll write a simple algorithm which will say, okay, this is where silence is, or this is where some scene transition happens. So I break the 3-hour video into say 1,000 scene transitions or 10,000 scene transitions. Then each scene there could be multiple sounds. Sometimes there is one sound in the background. So construction of the data is easy. I mean, once you correctly construct the data with each small snippet of audio with its own textual description, footstep of somebody walking, or a person with large heels walking, making sound, or bell ringing and all that, right? So that part is difficult. So once you have, I mean, otherwise acquisition is not a big deal, right? Today there are enough systems and audio and other things. Acquisition is easy. Labeling is the toughest part. But I think now there are a lot of open source data sets if you want to prove a certain architecture, right, your objective here is to say that, hey, I can use this perceiver resampler for audio also and arrive at a much low cost algorithm than say somebody else doing with some other more complex method. Then you just downloading those internet data and proving on those internet data that your algorithm is running fine, your architecture succeeds and it is running at much better accuracy, if not same accuracy and much lower cost. That part, I don't think you have to struggle with the audio gathering today. I think we have enough audio data sets.
Sir, for this classification, how can we classify, sir?
You will have to manually sit and label, right? I mean, technically, how is it possible? Or you're saying how to get a data like that?
Humans and animals like this, sir.
Yeah. I mean, unfortunately, you will have to either manually see. There is a bird audio detection challenge.
Sir,
So maybe they are, let's see what this is, right? So this, if you get something like this, you are lucky because already it is there, but then you'll be only able to show a model across those, right? So pre-collected data sets are good to prove your architecture or your design or your algorithm. They are not, unfortunately, they are not good if you are building an application or custom use case for it, right? Like a pressure cooker sound, you might not have any data set in the internet which will have it. Or if you want exactly for a buffalo and cow, maybe you don't have. Right? That's the problem. If you have something, if you're luckily your use case and some, okay, see, I think music, songs, some instrumental classification, and luckily for in our case birds. See, there is some urban sounds 8K also, so I don't know what is urban sounds 8K. So it contains 8732 label sound excerpts. See, good thing is each of them is less than 4 seconds. So that is what it is needed, because as the duration increases, there is a risk of corruption. 2, 3 sounds coming together, especially in the urban environment that we live, you can't control outside sounds. Then you have to go to a soundproof room. So it says these 873 samples, 8,000 samples are across air conditioner, car honking, children playing, dog barking. So if you want to prove your architecture on this and show that it's scoring more than anybody, or the accuracy is more, then these are good data sets to start with. I think they're easily, you may need just some request form to request it, but we are good. So there is one more here. Okay, luckily there are some animals, right? So you have dog, rooster, pig, cow, frog, cat. So these are things that you can use. Get this. I think they have published some methods also here. See, some papers which have given some accuracy on this data set also are there. So you can try and use this or build a use case or prove that you are getting this much, but then compute cost is way, way low. Any other questions? So I think it pretty fast built up. This whole WAV file is there. I think this is the sampling rate, 22K or 16K, and then you already have these ready-made packages with which you can. Okay, I think in this case they are creating dummy. Okay, this ran because there was dummy thing there. and it generated text. And then they're saying you need to run this. Pursuer is not defined. So that's the problem. Okay, this base module itself is not there, is what it is saying. Okay, maybe now the package has changed. Maybe this is old. But yeah, so this is the flow. The other one that we had was fast VLM. And here also, if we can. So this is one simple setup. Let me see if I get some GPU quota now. Try and run this. So okay, while it gets ready, maybe I will. So this is the fast VLM. Like I said, we can do it on CPU. Let's see if we are able to. So it's very few lines of code, right? Because now Hugging Face has really made it easy. So I'm importing Torch. This is for the image processing. And this is where the model and the tokenizer gets loaded. Now we know that for each model, there is a specific tokenizer which will convert the text into tokens. And you could have, so basically the model name is specified here. And I've given my token from Hugging Face. And the model loading, again, it will download the model. We'll see those prints coming through here. And we have specified, we've made a simple flow, right? The role is user and the content is this image, describe the image in detail, that's all. This is the pattern or flow that we are doing here. And then we apply the chat template and then run the inference. That's all is happening here, nothing major to capture here. So as we speak, it started downloading this model. It connected to Hugging Face. It has downloaded this. Right now, I think it just downloaded the tokenizer related parameters. Now it is downloading the actual model weight. So these safe tensors are actually model weight. So each of them is like 1.5 GB. And I think there are 4 or 5 of them. And remember that this entire thing runs on CPU. So I don't have GPU budget at all. It ran it, downloaded and loaded it. Let's see if it can process this bit. See, the result has gone well. you could see that it's a simple image loading from an URL workflow. Okay, it ran. So it took around 1 minute and it ran and it already said the image depicts a fox-like dog sitting in the forest setting. The dog has light brown. It gives you this elaborate description that you want. Now, let me see if we can change this message template. And we could try any other image if you guys would like to try here, right? Just give me an URL. And the good thing is you could just get it running on your machine without much. I think it takes around a minute for this 500 million, right? Half a billion, 500 billion, 500 million model. So I asked how many animals and plants are there in the scene. It says in the image there is one animal which is a dog which appears to be a corgi breed. As for plants, the background is filled with tall trees which have pine-like appearance due to the visible needle-like leaves. However, they do not appear to be any clearly defined flowering plants or distinct species. So basically, it has got this flow right. And so animal, corgi is their plant. There are no clearly identified flowers, plants in the image. That's what it is trying to say. This is the architecture. So this way we can do. So here I had created a setup where you could load any image and try. So let's see if this goes through. This is a different set of models. These are also slightly simpler. We'll see if this goes through. So here, if you see, if you choose model called blip, I think this is slightly enhancement or modification of a bird model where the image tokens are also inserted. So it's an image captioning model. LLVA is again a vision language model. And there is an instruct blip also. So this setup, I mean, now with Hugging Face ecosystem, it's very straightforward. Just mention the model name, it will connect, it will load, and you are okay. So this already ran. It took 42 seconds for us to get this entire definition all going. And I think successfully loaded the blip model. And now, test this. So the good thing here is I think I can, with the button, see, with the button, just choose any other image. Upload. Let's select something. Let's see for a slide what it does. So this is the one. In the caption, does it say it's a slide, it's an architectural diagram? Okay, I see a question called how to calculate confusion matrix for, okay, okay, see, good, okay, transformer, it's getting the spelling of the transformer wrong. So vision transformer, okay, maybe it is just reading the vision transformer at multiple places. It didn't get the, it didn't get the classification correct. So we could see that instructor. So both of them are running. So there is a question on how to calculate confusion matrix for different images. So I think maybe the question is, it is not about different images. So let's say you have 4 classes, right? You have 100 images, or confusion matrix especially is very important when you have class imbalance. So if you have like 4 classes, let's say dog, cat, buffalo, and cow, and buffalo and cow have lesser number of images than dog, cat in your both in your training and even in evaluation set, because you're not able to sample them so much. So then simple accuracy across how you classified, how your model after training classified them just by one number will not be a good one to do. So maybe I'll just go through that. So what you will do is you create a matrix. You create a matrix and you specify of, let's say your data set has, your test data set has 100 cats, 100 dogs, but only 20 cows and 20 buffaloes. If you blindly do the accuracy, then the total number of samples you have is 240. And even if you get all the cows and all the buffaloes wrong, you will still read it out as a high accuracy, which is not true, right? Because you got all those 40 cows and buffaloes wrong. Only these 200 you got. So it's like 200 out of 240 is still a high fraction, high number, but that doesn't throw a good picture. But now if you check using a confusion matrix, so basically what it does is it says out of those 20 cows, how many did the model get correctly as cow? And then it will also say where is the spillover. Let's say there is some problem only between cow and dog. So then in that confusion matrix, so it's a simple matrix, right? So maybe I'll fill it here, or I'll just write it off. Right, very easy. Like this is one very easy example, right? So what was actually spam? So in this case, let's say you had 20 cow images. How many actually correctly got classified as cow? And how many got classified? Here they're only shown non-spam, the 2 categories, but in our case, if it is those 4 classes, you will have those cow, buffalo, cat, and dog. So then what is truly classified as that will show up here, and you get other count. So one good thing you'll get is you will get something called precision. So you'll get something called recall. So out of actually cow images, how many really got classified as cow? So that is a very good number for you to really understand. And with this confusion matrix, you will also understand spillover. So here, if you see, you knew that there are 900 actually spam messages, but if you see prediction, 600, only 600 of them got caught as spam. 300 did not get caught as spam. This is just 2 class, but if you have multiple classes, it will tell you where your model is weak and across what classes it is confusing itself. So confusion matrix really becomes very, very useful in understanding your model's behavior. Instead of just going by one accuracy number or vanilla flow. I think that is what it comes to. But I think there is enough literature now to understand that. But more than theory, especially if you are building in your projects, if you have multiple classes, and then obviously each class will not have the same number of samples, both in your training and in your test scenario. So just don't go by a vanilla accuracy number. That could be pretty misleading. create that confusion matrix and then look at that. So going back. Okay, so this is what was there. Okay, it's not letting me choose another file. I don't know what happened. Completed. File.
Sir, only one type of image can you find the confusion matrix, sir? Is it possible?
No, one class of
Only one class, like only dog or only cat
okay.
or
So
cat of it.
see, first of all, when you have something like this, you're not building a conventional classifier, right? Because what are you? It's like no dog and no dog. Let's say
Sir.
like that. So now the problem is in the no dog side, it's like the negative side. Uh,
Huh.
you will need to put a lot of things, right?
Sir, in research, we'll be taking only one kind of data set, no, sir. Like dog means we were working on dog or a cat. If we have to take the like images only, for that, how to is it possible to calculate the confusion matrix?
No, there it is. There is right away. See, the general metrics that there is the precision and recall. You just say like spam is also one class, right? You're interested in spam, so
Huh.
same analogy holds here. Spam no spam and dog no dog, and then you could just say if you had, let's say you took 100 images of dog images of dog and images of other animals or nothing in the scene, right? So you will write dog, no dog as the actual, the way actually how many images are there, and then how many the model really called it as dog and no dog. So that's all, right?
Thank you,
Say
sir.
100 images of dog and 100 images of no dog. Out of those 100 images, how many did the model say correctly as dog, right? And similarly, you had given 100 of no dog, but some of them, if it still says as dog, maybe there is some other thing, animal or something that looks like dog. So that is why, see, the name is also very indicative, right? When spam is correctly specified as classified as spam, it is called true positive. When something is not a spam, but it is classified as spam, so non-spam is classified as spam, it's called false positive. So you could construct it, but slightly, what will you do with a classifier? You could build an LLM to say, hey, do I see a dog in or not? But otherwise, I'm not sure about the scenario.
Thank you, sir.
Yeah, so there is one more question from Pooja. So if the test image has more than one similar object, okay, test image has more than one similar object, accurate identification of the object will be done. So if I understand correctly, let's say there is minor variation in the breed of dogs, and then will we be able to tell apart or not? Is that correct? Or both objects are there? I'm not sure which one was the question. More than one similar object.
Good evening, sir.
Sorry?
Good evening, sir.
Good
Sir,
evening.
like if the objects are they are overlapping little half of the dog and the other breed of the other dog has been overlapped. So that
Oh,
time identification of the object, whether it will be done accurately or no.
no, then it won't be done accurately. So that is
Hmm.
we go through object detection and try and segregate them and all. So one is occluding the other, or one is partially exposing the other, right? It won't. That is one thing. Even after that, see it also, when you're training the model, have you exposed the model with this fine grain variation? Have you trained informing the model that these minor variations, maybe the shape of the ear of the dog or whatever, uh, it should be able to pick it up, and you should have those labels. Otherwise, the model will not be able to assess that. One strategy that they do is, see, so there is something called an open set problem. Let's say you did a lot of hard work and you collected photos of say 1,000 breeds of dog, or say 100 breeds of dog, and then it still doesn't guarantee that you will not uncover a new breed. So you want, okay, I built this, but at least it should tell me that it's not this 100 breeds, it is some new breed that I've not seen. So that is where instead of going for a general classification task, when you want to cater to open set recognition, they call, right? There you go for contrastive learning. So what you do is there is something called this triplet and metric learning. So where you take two images of the same breed of the dog, slightly different poses, or different dogs of the same breed, maybe slightly different age. And then this is the embedding generated out of that should be very similar, like the dot product should be low. Then you take another breed and then you say that the embedding generated for that should be far. So what you're doing is you're not learning a classifier, you're learning to generate embeddings which is distinctive of each breed. So when you do that, at least you will have an additional signal that now your classification doesn't become vanilla classification, it becomes like a dot product and lowest score and all that. So that becomes an open set flow where even a new breed of dog comes, you'll be able to handle.
Okay, sir. Thank you, sir.
So just read up on metric learning. You'll be able to understand metric learning, and specifically this technique is called contrastive learning. I think that is it. So they say how to learn without labels. So just go through that and we'll be able to get going. Are there any questions that you guys may have? So knowledge distillation is something that is going to come very handy, especially in projects that you do, because you want to show lightweight things. So here is an example where they trained a very lightweight bird model. They did not just match the output in terms of the probability, but they tapped out signals in between layers and also tried to match them across the teacher and the student model. And that is where they got really great accuracy even with small architectures. That would be something to try. The only thing here is these all are slightly big models, so they take time to load and all. So anything that we could have quickly ventured out, like trying to train a model is not gonna happen in a workshop session or half an hour or 1 hour session. So otherwise we could have tried something very useful. Any other question or anything you want me to capture in detail?
Yeah, good evening, sir.
Yes, sir. Good evening.
Yeah, I am Dr. Kumar Patil. My question is whether we can use confusion matrix beginning of the research or end of the research?
As in, sir, when we train a model,
Mm-hmm.
we want to evaluate its performance.
Okay.
So when we want to evaluate its performance, instead of looking at a vanilla accuracy number,
Mm-hmm.
it's better to put the confusion matrix and then see the spillover, right? And especially multiple classes, it becomes that much more important. More than binary,
Mm-hmm.
multi-class becomes important. So the research part is this, sir. So now, when you get a certain accuracy, either the model is lacking. So maybe all this uh, variance and bias aspects. Maybe
Okay.
you should build a larger model. So that is one angle, or your data is not sufficient.
Okay.
So this will confusion matrix is also key when you analyze and see that, let's say everywhere else accuracy is good. So some select 4 or 5 classes, the accuracy is not good.
Okay.
Means and there also the accuracy is losing because there is a spillover only between those. So all the wrong misclassification is happening between only those 4 only out of those 10.
Okay.
Then then that is not indicating on the architecture of the model.
Mm-hmm.
Then it is indicating that there is something in the data. Either those classes visually or in whatever modality you are, your signal acquisition system, the sensors readings there for those 4 or 5 scenarios are very similar.
Mm-hmm.
Or we haven't captured enough variety or variation. Like, say I mean, just the dog is in the scene, so I'm using dog. So
Yeah.
let's say you took the dog in only similar certain breed of dog, you have only taken in one pose, unfortunately, right? Because all images you collected is that way.
Okay.
So it could be lack of, so it could be, so the good thing is if you're seeing accuracy in the other 10 classes well, but these 4 or 5 classes are the only one who are pulling you down in terms of overall performance, then it is most likely that it is not the model that is the problem, it is the data that is the problem. So either it is the representation of those classes or the variety in which you have represented those classes, or those classes themselves are visually very similar or have minor variations. Now, those are big clues because that will not help by simply some training, changing some training parameters or tweaking your model architecture. You have to really nail them in you have to really nail them in your data collection.
Okay.
And some very minor variations, then you have to really, just because of those three classes, you will have to think of going for high resolution. Let's say some dog breed has some small dots in the ear which other breed doesn't have. If you want to classify, then like if you're building a convolutional neural network, there is the aspect of receptive field. What input resolution will you do for the detail to be caught? So it will throw light on all of those, so I mean it's a continuous thing. I think it's not like,
Okay. Thank you, sir.
so I think today's world, right? Most of the proven architectures you will get. So I mean, big companies have already engineered a lot of architectures. But sir, the problem is about your data. Generally, data is the biggest problem than your this one. Okay, so there is a question on how does TinyBird maintain accuracy while reducing model size for use on limited devices? So that is the theory or concept of knowledge distillation. So when you, the thing is this, so when you, let's say you want to classify a wheel, you want to classify a circle or a square. If the image has only possibilities of these two, you will write your hand-coded rules that I need some arches or curves everywhere, and they should be joint and all that. For a square, you will say I need straight lines or vertical or horizontal lines. That is the rules that you write. Now, when you take a convolutional neural network or of these bigger birds and all, there are very top level motivations, right? Just mask level modeling. So you mask out few words in between and ask the model to predict them. In the case of bird, or in case of GPT, it is the next word prediction. Now you are only giving that very top level thing and giving a big model and saying, okay, just learn this. Now when you do now take that and now we also said each model based on its size has a certain limited capacity in learning. Now, what is that extra signal or extra information you want to give to this chota model to really learn as well, or at least for limited domains, as good as a large model? So that is where, so when you train a model, how are you training? You're just giving a classes. So it's a binarized class, right? If you have 4 labels, 4 classes, if there is a dog in the image, you give 1 to the dog and 0, 0, 0 to other 3 animals. But let's say you are getting some additional learning methodology or technique or tricks from the large model. Now probabilities, instead of directly giving 1, 0, 0, 0 as the label and ground truth to the tiny bird or the student model, you see with what probabilities the large model has given. So maybe it has given dog as 0.9, but for the same image it has scored uh, say a buffalo, because it was black dog. Say buffalo is 0.09. So that is the closest, and others have hardly scored. So now you're getting a hint on not just what the large model is doing, but you are getting some insights on how it actually learned, right, by looking at those probabilities. So now instead of training the small model with simply the data set, you're taking those probabilities. You're not taking 1, 0, 0, 0 now. You're taking 0.9, 0.09, maybe 0.001, and then 0.0001. And now when you train with that, you are getting additional tips and tricks of how the large model trained. So likewise, in between layers output also, if you take, that is giving extra motivation or extra additional information to learn, use those in whatever limited number of transformer blocks, decoder blocks, or convolutional layers that the smaller model has more efficiently to mimic or imitate the learning of this large model, and hence they are able to do that. So there is a lot of literature on different techniques and how they have helped in this manner. So, anything else you want to know? So I would recommend, I'll put all of these papers. I would recommend all of you to go through. I think these will really help projects, especially in this domain, computer vision, multimodal, multiple sensor fusion. So please read up this paper. Let me see what else I can pull up here. Okay, so another thing is, today, if you want to try any model, it's very easy. I think most of you would be already well versed, but if you are not, Hugging Face already hosts a lot of these models. You'll be able to go to different companies, and each company's models, whatever they have, are all listed here. Like, this fast VLM that I said, from the smallest model, see, I think this may be much more smaller than this. So this, I think generally then it is FP32. So this is FP16. So you can take this, and already the code snippet to try is generally given. Okay, let's see, it's not given here. Okay, this model may still not be ready or something like that. Or they have given it for one. So, I mean, a lot of things are available for us to quickly try these days. So you don't have to really struggle. So, okay, like here they have given the code snippet, not much changes, right? You just need to change the model name here and sign in into Hugging Face, create an account in Hugging Face. And you are good to try quickly anything. So all leaderboards, all data sets are at your disposal. You can try the latest and the greatest model the day they are published. You don't have to wait for anything. So, and it also shows, see, like I said, mini CPM is already trending high, 13,000 downloads, which is what I showed, right? Because they've created the setup where you quickly get to try it and appreciate things. So there is one from Tencent. I think this is an image generation model, if I'm not wrong. There is other things, real-time video captioning, capture. Oh, there is one setup here. Right. Right. Oh, this is live captioning. So yeah, be aware of the privacy aspects, but otherwise this is good. So its camera is ready. You could do live. So I'm not keen on this now, but so there is a live one also that they're showing. So you can evaluate this model and see if it is good for your project, because anyway it runs. They claim it to run even on our mobile phone. So here is a data set, and whenever they release a data set, they call it a data card. Data set card for recycling the web. It has 44 billion tokens of high quality model filtered synthetic text obtained from recycling the web approach. And they have trained this Llama 3.3 inspect model. They've used this to generate the synthetic data. It just rephrases the information in web, I think. So the method to enhance pre-training data quality and quality of LLMs. Anything else you guys want me to cover? So by the way, this is the leaderboard, which they'll say who is the top scoring one now. So since no Gemini 2.5 Pro is coming top now, this is one more thing I think they have worked with. Let's see what it has to offer. So this is one more good model, and there are a family of them. And I think they have some quick deploy options, even fine-tune automated scripts with a click of a button. You can get going on these and start trying this. So I think, please bookmark these if you are in this domain of. Otherwise, we had other tools here. So a lot of internal models you'll see here. The language model used there is Quen. By the way. Vision model is intern VIT. That is one part. Gemini Pro is there. So I think here is one more. It's highlighting special capabilities. Okay, this is one more good thing which mimics human thinking, and it lets you go through the entire. If you ask how is Tesla doing, it will convert that into multiple questions to Google, run those Google searches, get the output, condense it, and then start giving you a flow. So you can see that, one simple text, it translated into all this, and then it gave a summarized response of this entire thing. So that is very useful set of things for you to really go. Right. Anything else that you guys want me to cover? We could have done a few more things if we had this GPU quota, but We don't have. So, looks like we can wrap it up. If you guys have no other questions.
Any other questions? Participants, if any other questions, sir will be there. I think it's done. Sir, shall we conclude it?
Yes,
Arun Kumar, sir.
yes, madam. We can do that.
Okay, sir. Okay, sir. Thank you, Arun, sir, for delivering such an insightful and engaging session. It was interactive too. And we hope the participants have got benefit of the about this multimodal AI using image, text, and all. Thank you. Thank you so much for your time and all contributing here. And thank you all the participants for your active participation in this 6 days ATAL FDP session. And tomorrow, I hope all of you will be joining in time at 6 o'clock. Thank you. Thank you, one and all.
Thanks, man. Thanks all.
Thank you. Thank you, sir. Participants are requested to fill up the attendance link. The attendance link is floated here. Just fill up and submit. Thank you.